There are three major theorems in this course yet to prove. So one of them is Urysohn lemma. It is basically it is a theorem known as Urysohn's lemma. So before going to the statement of the theorem, let us give one definition and then discuss the main question behind the theorem. Okay, so then we will state and prove the theorem. Okay, so recall that we have already seen separation of a pair of points, that is the notion of Hausdorff spaces. Okay, and also we know the notion of separation of a pair of a point and a closed set that does not contain the point. So these separations are by disjoint open sets. Okay, so the separation of a point from a closed set that does not contain the point, okay, by disjoint open sets, that is the notion of regular spaces, or T3 axiom. And also we know the notion of separation of a pair of disjoint closed sets in a topological space by disjoint open sets, and that is the notion of normal spaces. So here we define what is the notion of separation of two disjoint closed sets in a topological space by a continuous function. Okay, so here is the definition. Let A and B be two closed subsets in a topological space X, and they are disjoint, that is A intersection with B equal to empty set. Okay, so the statement is, the definition is, the sets A and B are separated by a function if there exists a continuous function f with domain on the topological space X and range closed interval 0, 1, okay, such that f of A equal to a singleton set 0 and f of B equal to singleton set 1. That is, for every A in the closed set A, f of A equal to 0 and f of B equal to 1 for every B in the closed set B. Okay, so this is the separation of closed set by continuous function. This is the continuous function, and A and B, these are closed sets, and this is the separation. So on A it is constant, so the restriction function on A, that is constant function 0, and the restriction of the function f on the closed set B, that is constant function 1. Okay, and well, note that, so on the codomain, that is closed interval 0, 1, this is subset of real line, and here on the real line we consider the standard Euclidean topology, and on 0, 1, closed interval 0, 1, we have a subspace topology of the standard Euclidean topology on R. Okay, so now the main question is, when every two disjoint closed subsets in a topological space can be separated by a continuous function. Okay, so this is the main question. So given topological space X and arbitrary disjoint closed subsets A and B, the question is, when does there exist So when there exists a separation, that is a continuous function f from x to close interval 0 1, so that the function restricted on a is constant equal to constant function 0, and the function restricted on closed subset b, that is constant function 1. Okay, so answer of this question, so Urysohn's lemma, basically Urysohn's lemma answers the question, and that is a characterization. Okay, this Urysohn lemma characterizes topological spaces where every two disjoint closed subsets can be separated by a continuous function. Okay, yeah, so we will give one more definition, that is definition of Urysohn function. So yeah, here is the definition. Let X be a topological space and A, B be two disjoint closed subsets of X. Okay, so X is topological space and A, B, these are disjoint closed subsets of X. So this is the setting. Okay, so in this setting, a continuous function f with domain x and codomain close interval 0, 1 with subspace topology of the standard Euclidean topology on R. Okay, so a continuous function, this is called Urysohn function if f of a equal to 0 and f of b equal to 0. Okay, sorry, f of b equal to 1. Okay, so singleton set 1, and that is the restriction of f on a equal to constant function 0 and restriction of f on closed set b, that is constant function 1. Okay, yeah, this is the definition of Urysohn function. So now in the notion of Urysohn function, one can ask this question, so as follows. So the question is, so now the question is, so when there exists, so consider the setting given topological space X and so any two disjoint closed subsets A and B in X. So when there exists an Urysohn function separating so A and B. Okay, so yeah, this is the refined question. So now before stating and proving Urysohn's lemma, so note that Urysohn's lemma has many applications. This is key in the proof of many other theorems. Okay, basically application of so these are implications, okay, of Urysohn's lemma. For instances, T's extension theorem, paracompact Hausdorff spaces equivalently admit subordinate partitions of unity. Okay, so the second one, so this is not in our syllabus of this course, but the first one, T's extension theorem, this is a part of our syllabus, so we will state and prove T's extension theorem. But in future course you will see, so there is so Urysohn lemma is a key point in the proof of the second statement. So paracompact Hausdorff spaces equivalently admit subordinate partitions of unity. Okay, yeah. So well, now we state Urysohn's lemma. Okay, here is the statement. Let X be a normal topological space and A comma B these are disjoint closed subsets of X. Okay, so they are closed subsets of X and they are disjoint, so their intersection A intersection B, that is equal to empty set. Okay, so this is the setting. Then so this is hypothesis. X, so X is normal space and A comma B, these are disjoint closed subsets of X. So then, so in this hypothesis, so what is the conclusion? The conclusion is there exists an Urysohn function separating A and B. Okay, and moreover, the converse is also true. Okay, so the converse is also true. That means, what is the converse? Converse is following: for every disjoint closed subsets A comma B, there exists an Urysohn function separating A and B, then the space is normal. Okay, that is X is normal if and only if every pairwise disjoint closed subsets of X can be separated by an Urysohn function. Okay, so that is the statement. So if and only characterization theorem. The converse part is easier. So let us prove the converse part first. So as I said, so what is the converse part? So our assumption here, for the converse part, our assumptions are for any disjoint. So for any disjoint closed sets A and B, there exists an Urysohn function f from X to close interval 0, 1 separating A and B. Okay, so what to show? We have to show that there are disjoint open sets U and B such that A contained in U and B contained in B. That is, there are disjoint open neighborhoods of A and B. Okay, so that is what to show. So the proof is, we have one line proof. Just consider U equal to F inverse close 0 and open half, and B equal to F inverse open interval open half and closed 0, closed 1. Okay, so this interval closed 0 and open half, that is open subset. So open subset, that is an open subset of close interval 0, 1 in the subspace topology. Okay, basically this is this is close 0 open half, this is equal to close interval 0, 1 intersection with minus open interval minus infinity comma half. So this is open. So this is open, and F inverse of this open set equal to U. So U is open because F is continuous, and similarly B is also open. Okay, and as this is a separation of A and B, so f of A equal to singleton set 0. So A contained in U, and similarly B contained in B. So U and B are open neighborhoods of A and B. So only to so that U and B, they are disjoint. Okay, so basically they are disjoint because this open set closed 0 and open half is disjoint from this interval open have a closed one. So therefore U and V they are disjoint. So this is the converse part. So this completes the proof of the converse part. So now we prove. So now we prove the main part of the theorem. Okay, so proof of Urysohn's lemma. So idea of the proof is following. Given two disjoint closed sets A and B in X, so the proof is in given in two steps. In the first step, we define a function. In first step, we define a function f from the topological space X to closed interval 0, 1, such that f of A equal to singleton set 0 and f of B equal to singleton set 1. And in the second step, we prove the continuity of f. Okay, so this is the idea of the proof. So to define function f, we need some construction. So preparation for defining f. We define, so let p equal to set of all rationals in the closed interval 0, 1. So here basically our goal is to construct a collection of open sets UR over R belongs to P. So for every rational number in the closed interval 0, 1, we construct an open set UR. Okay, for every rational R in closed interval 0, 1, we construct open set UR with the following property. For P strictly less than Q, we have UP closure contained in UQ. Okay, so this is the condition. So basically, here to construct such a collection, we apply the following theorem repeatedly. This is theorem 1. This is basically characterization of normal spaces. So this theorem we have proved earlier. Basically, this is recall. This is basically recall of characterization theorem of normal topological spaces. So a topological space, the statement is a topological space X is normal if and only if for every, so if and only if for every closed set C and open neighborhood U of C, there exists another smaller open neighborhood of C such that is denoted by V, such that so V closure contained in U. Okay, so V closure contained in U. So X is normal if and only if for every closed set C in X and open set U in X containing C, there exists a smaller open set V such that C contained in V and V contained in V closure and V closure contained in U. Okay, so V is open neighborhood of C, that's why C contained in V, V is open, and this is always true, V contained in V closure. Okay, this is always true, and so this condition should be there. The V closure contained in U. Okay, so this is the characterization theorem we have proved earlier. So this theorem we will apply repeatedly to construct such a collection. So first of all, you note that set of all rationals, that is countable set, and this P is set of all rationals in the closed interval 0, 1. Therefore, that is P is subset of set of rationals Q. Therefore, P is also countable. So as P is countable, so we can write the elements in P as a sequence P1, P2, P3, P4, and so on. Okay, without loss of generality, we can keep the first element P1 as 1 and P2 equal to 0, and then P3. So this could be anything. And the standard way of representation, the standard way of representation of the elements of P is following: 1, 0, then half, 1 over 3, 2 over 3, 1 over 4, 3 over 4, and so on. So this is standard way, so on. So basically we need this condition: first element is 1 and second element is 0, then this could be anything. So yeah, so you can write in this way. Okay, now we construct the open sets U R for every R in P. For R equal to 1, so for R equal to 1, that is P1 equal to 1, we define U1 equal to X minus B. Note that B is closed set in X, so X minus B, that is B complement. B complement is open. Okay, so B is closed, so B complement, that is X minus B. This is open set. Okay, this is open set. So U1 is open. Now, so for P1, this is defined now, U1. Now note that A intersection B equal to empty set. So therefore, A contained in B complement. Okay, therefore A is a subset of U1. Now we apply characterization theorem. This is closed set A and U1 is open neighborhood of A. Therefore there exists an open neighborhood V. Okay, open neighborhood V, that is open neighborhood of A, such that V closure contained in U1. So we denote that V equal to U1. Okay, so for closed set A contained in open set U1, we have V equal to U0, some open set, smaller open set, smaller than U1, such that U0 closure contained in U1. So that is the application of this theorem. Okay, so what we have, A is subset of U0 and U0 subset of U0 closure and U0 closure subset of U1. So this is U0. So applying characterization theorem, that is theorem 1, we have U0. So now U0 and U1, these are defined, that is UP1 and UP2, these are defined. Okay, so now we use induction. So induction hypothesis step is following. Let UPIs are defined for every PI belongs to the first n elements in this presentation. Okay, so UPIs are defined for every PI in capital PI equal to the first set of first n elements in P. Okay, now we prove. So now we go to the inductive step. So first define Pn plus 1. This capital Pn plus 1, this is equal to the set of first n plus 1 elements in P. Okay, that is P1, P2, and so on. Pn plus 1. So Pn plus 1, so that is in between 0 and 1, because this is rational in between 0 and 1 in the closed interval 0 1, and 0 is so P2 equal to 0 and P1 equal to 1. Okay, so Pn plus 1 has immediate successor and predecessor. So immediate successor is Q and immediate predecessor is P. Okay, so there are rationals P and Q in. So there are rationals P and Q in Pn plus 1 in this set, such that so P is less than Pn plus 1, less than Q, and these are immediate successor P. So Q is immediate successor and P is immediate predecessor. So in place of here, this should be Q and this should be P. Here we have a typo, please correct it. So Q is immediate successor and P is immediate predecessor of Pn plus 1. Okay, so note that P basically is less than Q. Therefore UP closure contained in UQ. Okay, so UP closure contained in UQ. So this is the condition. So for first n plus. Okay, so for first n elements P1, P2, Pn, we have constructed UPIs that satisfied this condition also. Okay, so so if P and Q are in so this is, again we have typo here, this should be Pn, not I. Pn equal to set of first n elements in P. Okay, so well so we have this is closed set UP closure, and this is open set UQ. So now again we apply the characterization theorem here. So we will get smaller open set that we denote by UN plus 1, that is smaller than UQ, such that its closure UN plus 1 closure that contained in UQ, and this is open neighborhood of UP closure. So we have this inclusions. So by applying characterization theorem, that is theorem 1, we get UN plus 1. Okay, so thus we construct UR, the set of collection of open sets for every R in P, and P is the set of rationals in the closed interval 0 1. Okay, now for every rational we have open set UR. Now we extend this collection to all over rationals by defining UR equal to empty set, and when R is strictly less than 0, and whole space X if R is strictly greater than 1. Okay, so now for every rational number we have open set, and that is basically UR for every rational in closed interval 0, 1, and for every rational negative rational we have UR equal to empty set, and for every rational greater than 1 we have UR equal to whole space X. Okay, now we are ready to define the function f. Okay, now we are ready to define the function f. So first we define for x, little x belongs to the topological space X. We define Q of little x that is equal to set of all rationals R such that X belongs to UR. Okay. Now we define f, that is function from x to closed interval 0 1 by f of x equal to infimum of qx. Note that for every x there exists some non-negative. So non-negative r such that x belongs to UR. So this for every x, qx is bounded below. Okay, so there exists some infimum of the set qx, and we define f of x equal to infimum of qx, and in more explicit way, infimum of the set R belongs to Q such that x belongs to UR. Okay, so this is the definition of the function. So and one can note, so one can say that for every a, so well, for every a qa that is equal to set of all non, so here it should be q belongs to R, so R belongs to Q, so little r belongs to set of rationals, so this should be script Q, so this is set of rational. Okay, such that R, this should be R greater than or equal to 0, because for R negative UR is empty set, therefore and U naught. So what is U naught? U naught is open set containing 0. So x belongs to A means x also belongs to U naught. Okay, so 0 should be so x belongs to U naught, and for every R greater than, so rational R greater than 0, so U not contained in UR, so that is the condition. This is the condition. Okay, so basically Q of A equal to set of all non-negative rationals, so this should be R greater than or equal to 0. So for every A in A, f of A that is equal to infimum of QA, and that is equal to 0. Okay, so f of A equal to 0 for all A belongs to closed set A. Therefore we have the first condition. Now for similarly, one can see that for every B, little b in the closed set B, Q of B that is equal to R belongs to Q such that R is strictly greater than 1, and so one can say that U1. So for every R greater than 1, basically B belongs to UR, basically UR equal to X. So B belongs to capital B means B belongs to X. Okay, so B belongs to UR for every R greater than 1, and U1 equal to X minus B. So U1 equal to X minus B. Therefore, if little b in B, then B does not belong to U1. Therefore, one note that for every little b in the closed set B, Q of B equal to set of all rationals get strictly greater than 1, and infimum of this equal to 1. So therefore f of b equal to 1 for all b in B. Okay, so we have these two conditions. So now what to show? We have to show that f is continuous. So once we show that f is continuous, then we can conclude that f is Urysohn function separating a and b. So f is function. First of all, here is the definition of the function. F is function, that is the restriction of f on a, that is constant function 0, and the restriction of f on the closed set b, that is constant function 1. And now only to it remains to show that f is continuous. So before going to the proof of continuity of f, we note this observations. So observation 1, and this should be observation 2. So what is observation 1? X belongs to U or closer. So x belongs to U or closer implies f of x is less or equal to R. So if x belongs to U or closer, then one can see that set of all rationals are greater than so set of all rational suppose denote this set of all rationals strictly greater than R, they are also in Q of x. Okay, therefore infimum of Q of x, that should be at least R. So f of x is less or equal to R. And observation 2, this should be observation 2 OB2. So if x is in U or closer, then every rational R prime, every rational R prime that is less than or equal to R. So R prime is not in Q of x, and so Q of x should be contained in set of rationals R such that R prime is strictly greater than R. Okay, and infimum of such set Qx is greater than or equal to R. So basically, well, I have not given the proof of these observations. So basically, one can. So this is an exercise. One can prove it easily. Let me discuss it once again. Okay, so if x belongs to U or closer, so U or closer, then for every rational R prime, consider U R prime. So R prime is greater than R. Okay, R prime is greater than R. Then U R closer contained in U R prime. That is the condition of this collection of open sets U R. And x belongs to U R closer, that means x also belongs to U R prime. So every rational R prime that is greater than or greater than R, okay, should also in Q of x. Therefore minimum of Qx should be less or equal to R. Okay, And similarly, one can say that if x is not in UR, then f of x is greater than or equal to R. So yeah, these observation, this is one, and this should be observation 2. So this will be used in the proof of continuity of f. So to prove the continuity of f, what we have to show? Suppose x naught is a point in the topological space X, and so f of x naught, that is in the closed interval 0, 1. Okay, now, and that is subset of R, set of reals. Now consider C comma D, an open interval in R containing the point f of x naught. So f of x naught belongs to open interval C comma D. So that means f of x naught, this is strictly less than D, and this is f of x naught is strictly greater than C. Okay, so in between C and f of x naught we have some rational. Okay, and in between f of x naught and D we have some rational. So because between every two real number there exists a rational. Okay, so well, let me repeat the first item. Let x naught belongs to the space X, and C comma D subset of this is subset of real numbers. This is open interval containing f of x naught. So what to show? We have to show that there exists some open set U in X containing little x naught, such that f of U is subset of C comma D. Okay, that would prove f is continuous. So here is the proof. Choose rationals P and Q such that P is in between C and f of x naught, and Q is in between f of x naught and D. Okay, so because f of x naught belongs to C comma D, so C is strictly less than f of x naught, and between C and f of x naught we have rational P, and similarly there exists a rational Q in between f of x naught and D. So choose any two rationals, such two rationals P and Q. Okay, and so from here you can see that f of x naught belongs to open interval P comma Q and open interval P comma Q. This contained in C comma D, open interval C comma D. Now consider U equal to UQ set minus UP closure. So UQ, this is open, fine, this is open, and closure, this is closed set. So open set minus closed set, this is open. Okay, so U is open basically. So our claim is U is this required U is required open subset of X containing x naught, such that f of f of U containing C comma D. So that we prove here. So first of all we first show that little x naught belongs to U. Okay, now by f of x naught. So what we have here, f of x naught less than Q. So f of x naught less than Q, that implies f of x naught less than q, and that implies x naught in u q. So this follows from observation 2. Okay, so one can prove it rigorously. Suppose x naught does not belongs to u q. So if x naught does not belong to u q, then f of x naught should be greater than or equal to r, q. But here we have f of x naught is strictly less than q. So basically negation of observation, so this is observation 2, so negation of observation 2 is is this statement. So by observation 2 we have f of x naught less than q implies x naught belongs to u q. So basically we have to show x naught belongs to u. So already we have shown that x naught belongs to u q. Now we have to show that x naught does not belong to up closure, because u equal to uq minus up closure. So now we have to show that x naught does not belong to up closure, and that follows from observation 1, because f of x naught, this is greater than p. Okay, this is greater than p, so p is less than f of x naught, and this implies x naught does not belongs to up closure, because if suppose this is our assumption, if x naught belongs to up closure, then f of x naught should be less or equal to p. So f of x naught should be less or equal to p, but p is strictly less than f of x naught. So by observation 1 we have x naught does not belong to up closures, therefore x naught belong to u. Okay, this is the conclusion. Now this is the last thing we have to show. F of u is contained in open interval c comma d. Now let x be an arbitrary element in the set u. So we have to show that f of x belongs to open interval c comma d. That would complete the proof. So if x belongs to u, then what we have, x belongs to uq, but x that does not belong to up closure. So because u equal to uq minus up closure, so x belongs to uq, but x does not belong to up closure. Okay, now x belongs to uq, and uq contained in uq closure, so x belongs to uq closure, and that implies f of x less or equal to q. This is straightforward application of observation 1. And x does not belong to up closure, that implies f of x greater than or equal to p. So this is also straightforward application of observation 2. Okay, so merging these two inequalities, we have f of x that is less or equal to q, and f of x this is greater than or equal to p. So we have this. Therefore f of x belongs to closed interval p comma q, and closed interval p comma q that is contained in c comma d. Okay, therefore f of little x belongs to the open interval c comma d, and x was arbitrary point in u. Therefore f of u is subset of open interval c comma d, and this completes the proof. Okay, so yeah, thank you.